Well, hi, good morning, and welcome to my shop. So, I've largely finished this radio, and I think what I'd like to do today is spend time kind of experimenting with the radio and examining its ability to reject images, and in fact, investigate this whole question around images and how they affect a radio. And I'm going to start out by saying that word image cost me probably 15 or 20 years of failing to understand what an image is, because it's not an image of anything, for crying out loud. Too bad they named that whole process that way, but I guess the world only has so many words, you know? But we're going to experiment with that whole situation. We're going to find out how much image rejection power there is in this radio, if I can do it. And then if things go well, if I manage to do this a little bit, and I can see my way through to it, I'll bring in another radio with a better front end and compare its image rejection. So that's my plan. Typically my plans last about 60 seconds and then something happens, and then I'm unplanned from then on. But let's see how far we can get here with doing some planned stuff. So just to explain what this is, in case you don't know what I'm talking about. Certainly not an obscure topic. I'm just going to make some scratchy notes on this piece of paper here. So, you know, the way these radios work is they convert the signal on the antenna through a very simple method of conversion. So you have a internal oscillator in the radio. I'm just going to draw a circle here and call it LO, producing a frequency that's controlled by the tuning dial. So when you're turning this, one of the things you're doing in the radio is you're changing the frequency of the local oscillator. So we have the reception range, if you like, the range of frequencies the radio will receive. An AM band, this is about 500 to 1600. And then we have an IF, almost like an internal radio built inside the radio that tunes only one frequency, normally 455 kilohertz, but it could be anything. But this is the standard, kilohertz. So the whole trick is to get the signal that could be anywhere in this range of 530 to 1600 and convert it to 455, where it goes through and comes out to the speaker, basically. And there's more going on here to get the speaker to operate, but that's basically what you're doing. You're using the local oscillator to convert it. Now, how does that work? How do you manage to convert it? So you have a tube. I'm going to draw it up here. So this tube in radios has varying names, functional names. In North America, commonly this is called the mixer tube. It's mixing a couple signals. It's going to mix the signal from the antenna with this local oscillator. And you just thinking about how I'm going to cover this. So this tube is called the mixer. It's also called the frequency changer. I think in England they tend to call it the frequency changer. That's a little more revealing of what it's doing. But it's doing all those things. It's mixing signals and it's converting them. How do you actually change it? How do you actually move the frequency from here to here? It's actually downwards too. How do you move it from here down to here? So you don't really move it or change it. You create another one. You create another signal at this frequency with exactly the same information in it, the same music, the same voices or whatever. And you discard the original one. The original signal, let's say at 640 kilohertz, that's a signal I often listen to here, gets partway into the radio and then it's just tossed aside. It's done. Because a new signal is carrying on that matches it, and that's this 455 one. This takes place in this mixer tube. Now if I draw the characteristic curve of a mixer tube, right? By the way, I'm going over all this to make sure I don't have holes in my own knowledge of it. So if we draw the characteristic curve of a typical electronic device. Okay. They don't all look like this, but the important thing is there's a flat area here in this curve, or a linear area, and then there's a non-linear curved area. There's one down here too. We're interested more in this. If you operate the tube in this area, which is normal, this is normally where everything's being operated, in this linear area, the signal you put in gets amplified, or whatever it is the tube is doing to it, and comes out just fine. If you operate up in this area, in this curved area, something funny happens. When you feed in your signal, this area will start generating harmonics. The actual wave shape will change. The sound you hear will change. So normally you don't operate up in here because it causes distortion, harmonic distortion. Now another thing you can do here, excuse me, let's say you have two grids in this tube. And you feed two different signals into it. Then out of the tube will come those two different signals, amplified, or whatever the tube is being used to do, typically amplify them. So the two signals would come out louder. Two grids, two signals coming out. But what if you push it up into this area of the curve? Well, something funny happens. You start getting lots of stuff coming out of here, but you get a couple of very interesting products, let's call them products, of the two original signals you've shoved in on these two grids. Along with the two of them coming out, you get the addition of the two signals. Excuse me. So if this is a million, and this is 1,500,000, you would get the addition. You would get 2,500,000, a signal coming out like that, and you also get the difference. So what did I say? 2 million and 1.5 million. If it was 2 million and 1.5 million, there's a 500,000 cycle difference between them. You'd also get a 500,000 signal coming out. 500,000 kilohertz. And you see how close the 500 is to this? If you can arrange everything just right, you can make sure that this is coming out. And your radio is sensitive to this. The radio really can't hear these other signals. It can't tune through them. To some degree, they're not even presented for other reasons I won't go into. So that's a whole deal. Now, how do you use a local oscillator to do this? So the local oscillator, let me give an example. Let's say we want to tune in this signal here. Let's say this is, 900 kilohertz. Got a nice radio station there. And we want to get the 455 to go through the rest of the radio. So we can stick two signals on here that are 455 kilohertz apart. They will produce a 455 to go through there. So it becomes kind of simple now. We just need this signal, the local oscillator signal, to be this distance away from that. So looks to me like if we can make the local oscillator run at 1355, the difference between these two signals would be 455. And this new version of the 900 kilocycle signal would start heading through the IF and heading for the speaker. So we can draw the chart for the local oscillator. I'm going to draw it something like this, showing the relative frequency range of the local oscillator. If you notice, it's just the AM band pushed higher by 455 kilohertz. So when you have the local oscillator down here, it can mix with a signal here and produce the 455. And up here, it's mixing with signals here and producing 455 again. Always producing 455. Well, won't the local oscillator mix with all the other signals? It's mixing with everything all the time. So the output of the tube, and I'm putting quotes around it, is this entire thing shifted 455 kilohertz. I really didn't draw the output of this. But a lot of those other signals, the ones that are far away from 455, are being suppressed in a number of different ways. So the radio tries to focus right in on the area of interest, and tries to, for a couple of different ways, it tries to push away everything else, or drop everything else, ignore everything else, or weaken everything else. So it's, if you tune to 900, although you're actually tuning the local oscillator to 1355, part of the radio's tuning will be right here. This is what this whole thing is about. This whole thing is about that. Not the whole thing. Now here's where the image comes in. So I mentioned that if you want to take your 900 signal and turn it into a 455, you set the local oscillator to 1355. Couldn't you set it to 455 below? What would that be? That would be 545. What if you could set it to 545? So if we had a signal at 545, I don't know, maybe here, pictorially, can't that be 455 away from there? And the answer is yes, it can. Yes, and you can tune the radio that way, and different radios have the local oscillator in different positions. Some may be above the target signal, some may be below the target signal. Normally it's above. Normally it's above because there's less chance of problems. I won't go into that any further, but normally it's above. So where's the image on here? Where's this image thing, this image problem? I haven't drawn it yet. Let's go back to trying to tune 900 with a high side local oscillator running at 1355. We can get another 455 signal out of this radio, an unintended one. If there's another signal out there in the world, another broadcast signal, really anything reaching the radio antenna, really, but another broadcast signal is what we're worried about. 455 kilohertz above this signal. It's another one up here. Let's just see, what would that really be? So 455 on top of this would be, I gotta do this. 1810. Now, if there's a signal at 1810 is going to be, my scale here is way off. So, but 1810 would be, well, the AM dial ends at 1600. So 1810 would actually be up here beyond the AM, beyond the range of the radio. If there's nothing there, if there's no signal there, there's no problem with this. If there is a powerful signal there, another radio station, a noise signal, who knows what, some guy on his ham radio, who knows what it might be, at that location, which is 1810, it has the potential to mix in the mixer tube with the local oscillator and produce another 455 signal, come through the IF and out to the speaker, and we could hear it. You'd be looking at the dial pointer swinging back and forth here while you're tuning, but you're actually listening to this. So what stops this? And the reason they call this the image is because you can think of the local oscillator as if it's a mirror and you have an image. But that's really a bad way of looking at this. This is really not the best way to look at it. The better way to look at it is the way I'm looking at it. You're hunting for this difference in frequency, thinking about it that way. Not thinking about some kind of mirror reflection image. There isn't any. There is none in here. Not really. So why don't we hear these? Well, do we not hear these? Depends on the radio. Now, a lot of radios, and all radios really, they should have something ahead of this mixer tube to reduce the amount of stuff getting to it, to focus the radio on this. This signal is going to come out nice and clean. This is an internal local oscillator. It's just a nice clean, there's nothing. This could be, how can I put it? the less of everything else and the more of the target frequency you can get into the front of your radio, the better off you are. So radios have a little bit of front end tuning. That's what this is supposed to symbolize. And the idea of this line is it's showing you how sensitive the radio is. So the radio is sensitive. It doesn't stop there. It doesn't curve back like that. It goes like this. It just goes down, 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 down. And same thing here. Down, 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 down. I think the rate of this downward slide is 6 dB per decade, I think. Not sure of that. So the signal here comes through great. Signal here a little weak because with the radio tuned here. With the radio tuned here, a adjacent signal here is weakened by this effect in the front end. And by the time you get way out here, this signal is so weakened it really can't get into the front end of the radio. And some radios really focus on this because the weaker the signal you're after and the stronger the image signal, the more difficulty you might have in hearing this guy. And even if this is the part that I just learned about the other day, it popped my eyes open, even if there's no signal here, there's noise here, just atmospheric noise and stuff, and that noise can come through, and even the noise generated within the radio circuitry itself can come through and appear over here as if it's coming from here when it's really coming from up there. So a really, really high quality radio tries to steepen this curve. So maybe they put a tube at the front end. So you have two tuning stages. You have the antenna, which is a tuning stage. Then you have a tube boosting it. Then you have another RF tuning stage. And what you're doing is you're just steepening this curve like this. And now, where this signal is, the radio's reception is way down here somewhere, making it much less likely you'd ever get a strong signal out here at this location appearing in the speaker when you have the radio tuned here. Now some radios are really poor on this, really, really poor. So let's say you get a radio with a back missing, and the back is like this kind of back here. Okay, the back of the radio had that on it. Okay, so that's not just a wild loop of radio. That loop of wire, rather. This is a carefully constructed antenna with a certain electrical impedance, a certain impedance on it. And this coil would be matching up almost certainly with the tuning capacitor. And that would give you some front end. That would give you this curve, if you like, this outside curve. But what if you picked up a radio at a yard sale and there's no back and this antenna is missing? And all you got is a piece of wire sticking out the back. There's no tuning from the antenna itself. And there's a chance in some radios, the cheapest, worst radios, that antenna would just be a wire, go right to one of these grids with no tuning. It means everything that's on that piece of wire, which it would extend right up shortwave, everything you can think of, stuck right on the grid there. There's none of this happening, none of this quieting out the other stuff. It's all there. And worse yet, if it all gets into here, it's all doing that mixing, dividing, adding thing. In a situation like that, with a radio like that, with very little front end tuning, you get all kinds of weird stuff. You pick up signals in the wrong place. You might pick up an AM radio signal 5 times higher than it should be. It can be a real mess. So when judging the quality of the radio, one of the things you want to do is figure out how steep is this front end curve before you get to the mixer tube, or how many stages are there ahead of the mixer tube. So we look at this radio right here that I've just been working on. And again, I'm going over all this very slowly and in detail, more for my own sake than for anyone who's listening. If I'm making mistakes, it's because I don't still have it all correct. And only one way to get it correct, and that's to work on it like I'm doing now. So, in this radio, the antenna comes into this capacitor right from the antenna, basically. The antenna is only a piece of wire, so where's the inductance to tune against? There's a coil underneath the radio. Remember that antenna coil? This one here, I think. It has another purpose too, and that's to isolate the antenna circuit away from the part of the radio. But that, let's take this off. So the very first tube the signal comes to is the 6SA7, and that tube, just double checking here to make sure I'm not wrong in what I'm saying. 6SA7. Yeah, you know what? We're going to jump onto the schematic. Now I'll talk a little more about this radio. Okay, here's the schematic. So let's just run through this again. So this is the mixer tube. This is that tube in my picture with two grits, and it really does have two grits. One is right there. Oops, upside down. Tube's upside down. One is right there. Where's that one go? Pin 5 goes down into the local oscillator circuits, and pin 3 goes right back to the antenna. So this is where the local oscillator is mixed with the antenna, right in this tube. This tube has to be driven into nonlinear operation, as I understand it. That's another part I don't understand 100%, but I believe that's the case. If this tube is operating in linear territory, it won't do what it's supposed to do. And usually it's the local oscillator which is overdriving the tube. And that's a bad way of putting it, but I think that's the way it works. So we come here and we ask ourselves, so how much of that special tuning is there in the front end of this radio to drive away unwanted adjacent signals? So there's some tuning right here with the antenna itself and this coil. Don't know if that's effective. This capacitor may be there to help with that. Don't know. Well, it just says M5500, so it's a 500 picofarad capacitor. Not sure. Who knows how many turns are in this winding and all that kind of stuff. But there may be some. There will be some kind of resonance here. And then here on this side of the coil, we have on this side of the transformer we have this coil, and this is the tuning capacitor here. So again, there's some of that rejection capability right here, and in fact it's sharp enough that they have to tune it and move it across the band. You can't leave this sitting, say, at 600 while you're trying to listen to something at 1200. You won't hear it at 1200 because this guy is snuffing that out. So this is not, these things are not boosting the signal. They are sharpening the response curve to the signal, or creating it, in fact, creating a response curve. You can pretty much put it that way. So the better this is, the better off the radio. Absolutely. So you notice the first tube encountered is the mixer tube. So this qualifies as a fairly simple radio, probably prone to some image problems. That's probably the case. And that's why I'm happy to experiment with this radio, because I realize that already, that it's susceptible. The last little AM radio I did has another tube out here before the mixer tube. And that creates the ability to sharpen the filtering. You could pretty much call it filtering out here. Sometimes this is called the pre-selector circuit, where you're trying to select the signal you want to present to the mixer tube. And the better that pre-selection, the less chance of the image showing up. And again, I hate to use that word image, the alternate signal from showing up. I can see why they chose the word image, because if you can understand the meaning that is applied to the word, then it's handy. But if you think it's a mirror image of something, it really isn't. Really, it's just, yeah. I wasted too much of my life trying to figure that out. Okay, so after this tube, out of this tube, potentially comes a whole raft of signals, one of which is 455. and will find its way through this transformer and on to the speaker. The rest coming out on the plate here, when they look out in when they look out in the radio that they're headed for off the plate, here it is here. This circuit looks more or less like a short circuit to ground. Short circuit. Is that the right way to look at it? A short circuit? Okay, I'm not going to dwell on this. Let's just say the raft of signals that are generated in this tube don't go anywhere in the radio. Just one makes it through, the 455 signal. Just a little area there I don't have a clear understanding of. So again, when you tune the radio, when you turn the knob, in this radio you're tuning two things. One is you're changing the frequency of the local oscillator, like that in all these radios. And you're also moving the front end tuning along. And alignment is getting these two things to track together, so they're at the right spot to work together. That's part of what's going on when you align a radio. If we had another front end out here, if we had another tube out here, and more filtering, more pre-selection going on, then probably this capacitor, the tuning capacitor, would have another set of plates, maybe 3 sets of plates. This one on this radio only has 2 sets of plates, a set here and a set here. See, they're connected by this dotted line, they're connected together. There'd be another one over here. And then you'd have the challenge of trying to make 3 things track properly all the way across the tuning range. And again, that's part of the radio design challenge. It's a big part of the radio design challenge. And the alignment that may be required to align these three things up. Now I have a military radio. It has 2 tubes before the mixer and 2 tuned stages before the mixer. And that results in an extremely sharp response curve. And that means the accidental sensitivity to, quote, image signals that might be occurring is greatly reduced. And what that allows in this receiver is to boost up the radio's sensitivity to something enormous. Without taking care of the image problem, having an extremely sensitive radio means you're going to hear a lot of images. And the thing, you won't really realize that that's happening. Not necessarily. You pick something up, something come out of your speaker. It sounds great. It's not where you think it is, though. So, and commercial receivers, military receivers, very high quality receivers have more and more pre-filtering out the front end here. All of it with the difficulty of tracking in the radio. So, what happens when this doesn't work? And how many ways can it not work? Well, in this radio we're looking at, there are none of these front end tubes. So in a sense, none of that is working. We have some passive stuff here, which is going to help. How good it is, though, I don't know. But that's what I want to try to find out. Now I'm going to go back to my little diagram there, and then we're going to start playing around with our radio, because, man, have I been talking for a long time this morning. 30 minutes I've been talking. Holy smokes. So I hope this is helpful. I know some of you know this stuff. You're going to know it better than me. And others of you will be like I was years ago. You hear about these things and not quite sure what's going on and can't figure it out, because there's a lot of things you have to know before you gotta have a lot of pieces of the puzzle in front of you before you can put it all together. Now, what was I going to do with this? So there's a couple interesting things here. The radio's reception range overlaps with the local oscillator. So you could potentially have a radio with a local oscillator running, let's say here, because you're listening to something on your radio here. Another radio can pick this up directly, can tune right here and hear this thing. I do this in my shop now and then. Once in a while you can be fooled by this effect if you have a couple radios going. When I'm listening to shortwave, I have 2 and 3 radios going, all hooked up solidly to the same antenna, and they are exchanging some of their local oscillator signals a little bit. So I pay attention to that kind of stuff. Now, so my first example, 900, 1355, 1810. You see 1810 is actually beyond the AM band. And what is out here? In my case, a lot of noise out here. Lots of noise. So there could be a big noise signal at 1810, but there won't be any radio signals. But what if we change this? What if we go from 900, let's say we're going to tune 600. That's an easy number to work with. 600. Okay, so to get 600, I'll write it up here, we would tune the local oscillator to 1055, 1055. 1055, if you add 455 to that to find out about sensitivities at the other end of the band, you would end up with, I'll write it over here, 1455. So I think it's 1510. If I'm wrong, it doesn't matter. Don't have to be exactly right. 1510. Now what if there's a powerful station at 1510? A powerful AM station at 1510, and I've got my radio tuned to 600. If that whole image rejection thing we've been talking about is not working well, you're going to hear it. So part of the images are coming from the upper part of the AM band, and the rest of it will be coming from beyond the AM band. Okay, I think that's enough. Now, if we want to try to play around with this radio over here, I think I would set up this exact scenario, the one I just talked about. We tune the radio to 600. We know the local oscillator should then be at 1055. And we know the radio is sensitive then to 455 above that, 1510. If I pump a 1510, if I tune the radio to 600, pump a 1510 signal into the radio, will we hear it? That's basically what it amounts to. Now the other thing about the AM broadcast band, and probably you've never thought about this, but it's 500 here, it's 1500 here, that's 3 times. That's 3 times. In terms of electronics, that's a lot of difference from here to here. And most radio bands other than the AM band here are not like that. Not at all. And why did I say that? I'm not sure why I said that. I'm pointing that out anyway. I think that's something to keep in mind. Now if we're looking at a shortwave radio, this one's not a shortwave radio, it's still using 455 kilohertz. The problem is, you could think of it this way. These curves, you could think of it as remaining the same while the band gets crunched down, down, down. And that's bringing this potential interfering signal closer and closer and closer, if you like, or further up under this, or under this, whichever one you want to think about. So, on these old radios, on the high end of the shortwave band, just keep going, Jim. On the high end of the shortwave band, 18 megahertz, 25 megahertz, whatever it is, in effect, the image is getting closer and closer and more under here. That's my understanding of the situation. Some of that, what I just said, I have some doubts about it. So I have doubts about a lot of the stuff I say. You should too. I know this: in a shortwave radio of this sort, where when you get up at the high end, all the frequencies are really crunched together, they're much more sensitive to image problems. Is that really true? Maybe I'll be able to figure this out. Maybe after I do this session, I'll be smart enough to actually examine this question on any radio that comes in here. Okay, let's throw that away. Let's follow that exact model. So we're gonna switch this guy on, get him warming up. What do we got going here? Okay, put the cabinet away here. That came out pretty good, eh? Lovely. So first we want to tune this to 600. No, I'm going to stop the video. I have another piece of equipment I want to set up in here too while we're doing this. So I'm going to stop for a bit, get a bunch of stuff hooked up here. Okay, so what you're looking at now in the lower right corner is another radio receiver, my SDR radio, which happens to have a really nice frequency display on it, which is what we're looking at. You can see it says 640, and you can see a red line. The red line is set to 640. That's what that radio is listening to right now, but we're not hearing it. Here, I'll just turn the volume up and you'll hear it. Okay. Now, we don't really want to listen to that radio. We want to listen to this one here. So there's something on there now that is coming from this radio. So you see the red wire here is the antenna to the SDR, and to the radio you're looking at on the screen, and it's just connected to this, just a bit of wire. That's all this is. I'm just shoving it in here, kind of near the capacitor, near the first tube. Now, if we look on the SDR itself, I'm going to tune the radio. With any luck, something's going to move on there. Here we go. Thank God something is moving. So that signal you see going back and forth is the local oscillator signal in the radio, right? This guy here. Now the radio is probably tuned to 640 or 590. The local oscillator is running at around, looks like 1050 or 1040. So what we want to do is we want to tune this radio to exactly 600. So to tune it to 600, the local oscillator should be at 1055. So I'm going to move the local oscillator to 1055 on the SDR. It's almost there now, isn't it? 1055. Okay, I'm going to make sure the frequency there. I'm going to set this to 1055. 1055. So that puts the red line. Oops. 1050. 1050. 1050. 1055. I think we know now why the 455 is not 450 or 460. Because with 455 and everything tuned up absolutely right, images will always end up between the AM stations. Is that true? I don't know. Sounds great though. So we'll move the local oscillator at rate of 1055. Well, I got it bang on right now. It's already tuned there. So what do we got? The local oscillator on 1055. With the IF at 455, the radio is now sensitive to any signal that might be at 600. We're hearing something. Are we? So 600 is very close to 590. 590 is a very strong signal. There it is. Okay, so I'm going to put this... Ooh, what was that? What happened? No! I think my radio just broke. My radio broke. Oh my gosh, not now. Well, that's interesting. Okay, so I have the radio completely isolated here. Still doing this. Okay. Wow. Isn't that... I tell you, man, these are evil, evil machines, because I was in a fraction of a second of actually testing the very thing I wanted to do, and then disaster struck. Oh my gosh. Well, I can't say I've ever had a radio break down right in front of me while I'm using it. That's a new one. That's a new one. I think it's an act of desperation from the radio. It did not, you know what? The radio did not want me to find out its poor performance on image signals. Well, this is another whole round of troubleshooting that's going to be required now. So I've already noticed that the volume control doesn't eliminate all that noise. Oh man. Well, what kinds of things go suddenly? Well, just about anything can go suddenly in here. The most likely thing is the tube, I think. The tube problem. Okay, I gotta stop and think about the situation here. This is not at all where I wanted my head to end up. Wow, this might be the end of this video right now, actually, because I've been in here a long time. So I gotta kind of apologize for having gone all this distance and then, you know, the payoff didn't come. Okay, now I'll just I'll calm myself down by watching some news. Sure. Okay, so this might be the end of this video. If it is, thanks so much for watching to this point. And I'll carry on.